This is Physics 104B at Porterville College, the Chapter 17 homework. We'll start with number 11. It says Mars's atmospheric pressure is about 1% that of Earth, and its average temperature is around 215 Kelvin. Find the volume of 1 mole of the Martian atmosphere. So we'll start by writing the given information. Pressure 1% times 1 atmosphere. And 1 atmosphere is 1.013 times 10 to the 5th pascals. So this will be times 10 to the 3rd pascals. I've written the temperature. We're dealing with 1 mole. So we're going to use PV equals nRT. It asks for the volume, so we will solve for volume of 1 mole. Volume equals nRT over P. Make sure that your units are all consistent. 1 mole times 8.314 joules per mole Kelvin. So the moles will divide out. Times 215 Kelvin. There you see the kelvins are going to divide out. Over the pressure, 1.013 times 10 to the 3rd pascals. That leaves you with joules per pascal, but you can do some dimensional analysis to see that that actually comes out to meters cubed. So 1.8 meters cubed, or 1,800 liters. Number 12, how many molecules are in an ideal gas sample at 350 Kelvin that occupies 8.5 liters when the pressure is 180 kilopascals? Because the question is asking about molecules, I recommend using PV equals NKT instead of PV equals nRT. We use nRT with the little n when we're talking about moles, and we'll use the capital N when we're talking about molecules. So PV equals NKT. And keep in mind, as I've written there in the light blue, that 1 liter is equal to 10 to the negative 3 cubic meters. Question asks for how many molecules, so let's solve for N equals PV over KT. So we plug in all the values given in the problem. K is your Boltzmann's constant. You can find that in the front flap of the book, 1.38 times 10 to the negative 23rd joules per Kelvin. And we end up with 3.2 times 10 to the negative 23 molecules. Number 13, what is the pressure of an ideal gas if 3.4 moles occupies 2 liters at negative 150 degrees Celsius? So we're dealing with moles. We're going to use PV equals nRT, and it's giving 2 liters as the volume. So let's think about how to do this. We have P equals nRT over V, and we could do 3.5 moles. We have R, gas constant, times the temperature. Remember, we're using a temperature, not a change in temperature. We're using absolute, so we need that absolute Kelvin scale converted to 123.15. But then, given that it's in liters, 2 liters, we need to convert that if we're going to make this equation work. So we have 2 times 10 to the negative 3 meters cubed, and we get 1.8 times 10 to the 6 pascals. However, you can see what I've written down there in the purple, an alternate constant that we can use for that gas constant. Look in the middle of the numerator. Since we're dealing with liters, we could also use this gas constant. It's a very useful one, 0.08205 atmospheres liters per mole Kelvin. And I recommend you might want to write that constant in the front flap of your book along with the universal gas constant R. And what that does, it enables us to not have to convert the denominator, to convert the volume to cubic meters. The liters will go away, but look at the dimensions. Notice moles go away, kelvins go away. Look at what we're left with. We're left with atmospheres. So we're left with 17.7 atmospheres, and that's a fine answer. But if you want that in MKS, you'll then have to convert that to 1.8 times 10 to the 6th pascals. Number 17, in which gas are the molecules moving faster? Hydrogen at 75 Kelvin or sulfur dioxide at 350 Kelvin? So we're going to look at the speeds of those. Now, we do need to keep in mind what the masses are. So if we're talking about hydrogen, that's going to be molecular hydrogen gas. 2 protons, and so it has 2 atomic mass units. Sulfur dioxide, we can look that up in a periodic table if we need to, but it's SO2. And S, the sulfur, has a mass of 32. Each oxygen is 16, so that's 64 atomic mass units. In section 17.1, you learned about the thermal speeds, and that's what we're going to use here. The thermal speed is the square root of 3 times Boltzmann's constant times the temperature divided by mass. The question is asking about the relative speeds, and particularly it's asking which is moving faster. So I would set this up as a ratio. There are different ways you can do it, but this is how I did it. So let's set up a ratio, VH over VS. So in this instance, as I'm setting it up, I don't actually care what their speeds are. I'm just looking for the ratio. VH over VS. So if the hydrogen is moving faster than the sulfur dioxide, then this will be a ratio that's above 1. If it's moving slower, then it's below 1. So I'm just going to check out the nature of this ratio. We have square root of 3K temperature of the hydrogen divided by mass of the hydrogen, divided by square root of 3K temperature of the sulfur dioxide over mass of the sulfur dioxide. A lot of things divide out. I've included them all in one radical. The 3's and the k's divide out. What we're left with when you clean that up is the square root of the ratio of the temperatures, TH over TS, times the ratio of the masses, MS over MH. So that ratio becomes, now I'm plugging in the values, 75 Kelvin over 350 Kelvin times 64U over 2U, and that gives me 2.6. So that tells me the hydrogen is moving 2.6 faster than the sulfur dioxide molecules. So the hydrogen molecules are moving faster. Number 23. You have exactly 1 liter of ethyl alcohol at room temperature, 20 degrees Celsius. You put it in a refrigerator at 2 degrees Celsius. What is its new volume? So this is volume expansion, or in this case, volume contraction. V naught equals, it says exactly 1 liter, so we're going to say 1.0000, a bunch of zeros, liters. You have your T naught and your T1. We look up ethyl alcohol, the contraction coefficient for volume is 75 times 10 to the negative 5 per Kelvin. The change in temperature is T1 minus T naught, so that's negative 18 Kelvin. I'm going to use this equation, V equals V naught times 1 plus beta delta T. And we plug in those values and we get 0.987 liters. So just by putting it in the refrigerator, it shrunk by a couple of milliliters. Number 30. This is based off of example 17.1 in the chapter. The solar corona is the sun's hot, diffuse outer atmosphere. Typical corona conditions include a temperature of 1 megakelvin and a density of 10 to the 8th particles per cubic centimeter. Make an order of magnitude estimate of the ratio of the pressure in the corona to atmospheric pressure at Earth's surface. Okay, so it's asking us to do an estimate. Let's do PV equals NKT here, see what we get. Let's get the pressure. And it says P equals NKT over V. So I'm thinking about 1 cubic centimeter, because that's the information given, and it says 10 to the 8th particles. So let's plug that in, 10 to the 8th particles in this cubic centimeter that we're thinking about. Times K, Boltzmann's constant, times the temperature, 1 megakelvin is 10 to the 6th Kelvin, divided by the volume. Now it said we're dealing with 1 cubic centimeter. Let's get that in cubic meters. You can see the conversion that I did down here, 10 to the negative 6 cubic meters. Make sure you remember how to do volume conversions. And so when we calculate that, we get the pressure is 10 to the negative 3 pascals. Now we compare that to Earth, which is roughly 10 to the 5th. It's actually 1.013 times 10 to the 5th. And we see that it's 8 orders of magnitude lower than the pressure on Earth. So the pressure in the corona of the sun is roughly 10 to the negative 8th times the pressure, the atmospheric pressure on Earth. Let's go to number 37. A compressed air cylinder stands 100 centimeters tall and has internal diameter of 20 centimeters. And there you see I've written the height is 1 meter, and I've written the radius is 10 centimeters. I've written it as 0.10 meters. At room temperature, the pressure is 180 atmospheres. How many moles of air are in the cylinder? What volume would this air occupy at 1 atmosphere and room temperature? Meaning we release it out into the open, and how much volume would it be? Well, you see I've got volume equals pi r squared h. That gives us the volume of the cylinder. And with that in mind, let's answer the question how many moles there are. PV equals nRT becomes N equals PV over RT. You can see the values I've put in for P. It's 180 times, but we need this in pascals. So 1.013 times 10 to the 5th pascals. We've got our volume. We have the gas constant down below, R. And the temperature, be careful, we need this in Kelvin, 293 Kelvin. So we get 235 moles. Now for part B, we're going to look at some changes that we're going to make. We're going to release it out into the open, so pressure and volume are going to change. What is not going to change is N, the number of moles, R, the universal gas constant, and the temperature. Because it says at room temperature, the pressure is 180 atmospheres, and then it says it's being released at room temperature. So temperature stays the same. I'm using the technique here where I put algebraically all the changing quantities to the left and all the constants to the right. And then I ignore those constants on the right. I'll just say that P times V equals constant. And I really don't care what it comes out to be. It's just recognizing that P times V is constant. Well, then I can do P1 V1 equals P naught V naught and solve for the final V. So algebraically, I do V1 equals V naught times P naught over P1, plug in those values, and I get 5.65 cubic meters. We go now to number 41. A stove burner supplies heat to a pan at the rate of 1500 watts. How long will it take to boil away 1.1 kilograms of water once the water reaches its boiling point? Okay, the water's already at its boiling point. We don't need to raise its temperature. We're just boiling it away. We're going to use Q equals M times the L sub V. And so the mass is 1.1 kilograms. We look up the latent heat for water, and we see the latent heat for vaporization, L sub V, is 2257 kilojoules per kilogram. That means times 10 to the 3rd joules per kilogram. We just multiply those numbers, and we get a heat required of 2.483 times 10 to the 6th joules. Now, if power equals Q over T, that means T is Q over P, doing the algebra. So we do the Q divided by the power, 1500 joules per second, and we get 1655 seconds, or 27.6 minutes. Number 43, a metal cutting torch produces 2.35 kilowatts of thermal power. Assuming that 45% of the torch's power goes into melting metal, how long would it take the torch to melt a 2 centimeter diameter hole through a 12.5 centimeter thick piece of stainless steel? The steel's heat of fusion is 268 kilojoules per kilogram, and its density is 7970 kilograms per meter cubed. All right, in this solution, you can see, first I've drawn a picture right there. I've written out the power, 2350 watts, but we're not going to be able to use that 2350. It says that only 45% goes into melting the metal, and so let's just do that multiplication. We get 1057.5 watts. I've written out all the given information, heat of fusion, and the density. Now to melt it, part of what I've written on this line where you see my pointer, we're going to ignore. So the heat is, first we need to raise its temperature, and then we need to melt it. The book does not clarify what temperature it's starting at, but the intent of the author is that it's already at the melting point. However, down on the lower half of the page, I've shown how much it would add if we need to use the heat to actually raise it up to its considerably high melting point. But the intent of this problem is just to deal with this the second part, the melting of it. So let's just deal with that, and then later on we'll talk about what if we need to actually raise the temperature. Well, we need to know the mass. Mass is density times volume. We're dealing with a cylinder. Volume is pi r squared times h. So the r, if it's 2 centimeters across, then that's 1 centimeter radius, which is 0.01 meters. The height is 0.125 meters. Make sure you're keeping straight your units. We need to have these in meters. What you should get once you multiply that volume by density is 0.31298 kilograms. Therefore, the heat to melt it is the mass times the heat of fusion, so 83,879 joules. Now we involve the power. We're able to use 1057.5 watts. That's what I got at the top of the screen there. Time is heat over power. So when you plug those in, you get 79.3 seconds, and that's the answer that's in the back of the book. However, more practically, I'm thinking, what if we need to use this blowtorch first to raise it from room temperature to the melting point? So before melting it, it needed a rise in temperature from 20 degrees Celsius, I'm presuming room temperature, up to the melting point of stainless steel is about 1400 degrees Celsius. And so we need Q equals mc delta T. We have the M for steel given in chapter 16. The specific heat is 502 joules per kilogram Celsius degrees times the change in temperature going from 20 to 1400 is 1380. And it takes 216,820 joules. Well, that isn't negligible. If you compare it with, up in the middle here, what we got for the heat necessary to melt it, 84,000. So if we are going to include the raising of the temperature, it is substantial. Well, to raise the temperature, the time Q over P is another 205 seconds. And so if we need to raise its temperature from room temperature up to melting point and then melt it, it becomes that 205 plus the 79 we got originally to melt it, so 284 seconds. Number 47, how much energy does it take to melt 12.5 kilograms of ice initially at negative 10 degrees Celsius? So we have to think about the stages it goes through. A stage will be either a change in temperature or a change in phase. So I've written them out one by one, as many stages as it goes through. And first we have ice, whose temperature needs to go up from negative 10 degrees Celsius up to 0 degrees Celsius. At that point, temperature stops going up and it melts. And the question is asking how much time does it take to melt? So we're not going to take the temperature beyond 0 degrees. We'll need the specific heat of ice, 2050 joules per kilogram Kelvin. So the heat required is the heat to do step 1 plus the heat to do step 2. Step 1 is a change in temperature, so mc delta T. Step 2 is change in phase, so m times the latent heat of fusion. If you want to, you can do as I did, factor out mass. And so you can see I've plugged in everything. The change in temperature here, it's a rise of 10 degrees Celsius, or 10 Celsius degrees, because 0 minus negative 10. I wrote 10 Kelvin just because the units in specific heat, I've written those as Kelvin. I wanted to have some consistency there. But remember that if you're talking about a change in temperature, 10 Kelvin is 10 Celsius degrees. And then we have the latent heat of fusion, and we get an answer of 4.43 times 10 to the 6th joules. Next is problem number 48. Water is brought to its boiling point and then allowed to boil away completely. If the energy needed to raise the water to the boiling point is 1/10 of that needed to boil it away, what was the initial temperature? All right, so it's going from some T, I've underlined it, that's the T we're going to solve for, up to 100 degrees Celsius, that's step one, and then it's got to boil. Well, we can say what we know from the problem is that Q of step one is equal to 1/10 of Q of step two. The energy to raise the temperature is 1/10 that needed to boil it away. So we start by setting up this equation, and now we'll make substitutions. So Q1, we'll say MC delta T, is 1/10 of Q2, which we'll say is MLV. The M's divide away. Now I'm going to break down that delta T because it's the T that's embedded in it that we want to solve for. So that's going to be the final temperature, 100 degrees Celsius minus T. And whatever T we solve for, because I've chosen to do this in Celsius, it's going to be a Celsius answer. I could have made that final temperature be 373 Kelvin. And in that case, our answer would be Kelvin, but let's stick with Celsius here. We can do that. On the right-hand side, LV over 10. And I've divided away the C from the left-hand side and therefore from the right-hand side. So when we solve for T, doing a little algebra, T is 100 degrees Celsius minus the heat of vaporization divided by 10 and the specific heat of water. So we plug in the values and we get T is 100 degrees Celsius minus that fraction becomes 53.9 degrees Celsius. So we get an answer of 46.1 degrees Celsius. Here we have the final problem, number 59, a steel ball bearing encased in Pyrex glass, 1 centimeter across. It's a glass cube. At 330 Kelvin, it fits tightly inside the cube. At what temperature will it have a clearance of 1 micrometer all around? You can see the picture I've drawn. Here, the steel ball fits perfectly inside, a length of L0, which later we'll substitute in as 1 centimeter. And here I've drawn it 1 micrometer on each side. So there's the Pyrex has to be larger than the steel by 2 micrometers. Now I drew the picture bigger, the second picture bigger, and that implies that it has grown, that everything has grown, but that's not necessarily true. In fact, just the opposite is true. You can see that Pyrex has a coefficient of linear expansion of 3.2 times 10 to the negative 6. Steel is 12 times 10 to the negative 6. Steel has a greater coefficient of linear expansion. So if we were to heat this up, they would both grow, but the steel would grow faster than the Pyrex, and it might break through the Pyrex. So actually, we're looking for a decrease in temperature that'll make them both shrink. And in shrinking, the steel will shrink faster than the Pyrex and allow those gaps. So the second picture actually should be smaller. But sometimes you don't know that going into the problem, so this is how I've drawn it. All right, let's look at this. We're thinking about the length across. Even though these are three-dimensional objects, we don't need to do volume. It's not appropriate here because we're looking for the length across. So ultimately, we're looking for that the length across the Pyrex is the length of the steel plus 2 micrometers, 1 micrometer on each side. We do these substitutions. L0 1 plus alpha Pyrex delta T equals L0 1 plus alpha steel delta T equals 2 micrometers. I don't have subscripts on my delta T's because we don't have to distinguish the temperature of the Pyrex versus the temperature of the steel. They are the same thing. They're at the same temperature, so we'll just say delta T, and that'll make the math a bit easier. Let's combine those terms on the left-hand side. Before they're on the left-hand side, going from this line, we need to subtract away. I want to subtract away the delta T term on the right-hand side because I want all my T terms on the left. So I'm going to subtract away from both sides L0 times 1 plus alpha steel delta T. Now I'm going to combine And so it's L naught times 1 plus alpha P delta T minus 1 minus alpha steel delta T. The ones will subtract away, and we're left with, on the right-hand side, L naught times alpha P delta T minus alpha S delta T. And in the line where my pointer's at, I've just divided both sides by L naught because I want to isolate T. I want to get everything that is not T over to the right-hand side. Now, on the next line, I'm going to factor out delta T. So we have delta T times alpha P minus alpha S equals 2 micrometers divided by L naught. Then I'm going to divide both sides by alpha P minus alpha S, and that gives me delta T all by itself. Now, before I go on and plug in values, I just want to point out this interesting parallel. This equation where you see my pointer is at looks like delta T equals delta L over L naught delta alpha. Now, delta L, that's not a change in length. In this case, it's a gap. It's a difference in length. And delta alpha is a difference in alphas. But I just find it interesting that this equation looks a lot like the equation given to you in the book, how alpha relates to the change in length and change in time. All right, let's go back to the problem here, though. We plug in the given values. Make sure that for L naught, it's 1 centimeter, but let's have it in MKS units, so 10 to the negative 2 meters. And we get delta L is negative 23 Celsius degrees, which is also negative 23 Kelvin. We're looking at a change in temperature. So it drops 23 degrees, whether you're talking about Celsius or Kelvin. And this is what I expected in the beginning when I saw that steel has a higher coefficient of linear expansion than Pyrex. If we did heat it up, the steel would get bigger than the Pyrex. Well, we want a case where the steel goes smaller, so necessarily we need to decrease the temperature, and that's what we see here. It's a drop of 23 degrees. Well, the question is asking what is the temperature where that occurs. So the final temperature is initial temperature plus the change in temperature. So the initial, which is 330 Kelvin, plus the drop of 23 Kelvin, and you get 307 Kelvin. And that is the end of the Chapter 17 homework. Have a great day.